So yesterday we stopped at this point where we identified like 10 pairs, 10 possible gender pairs, and from here, like the idea was to evolve a gender subspace. Okay, so these 10 gender pairs that were identified. So the first thing that the authors did was that they tested how good these gender pairs are. And in order to test this, they looked for the 100 words, out of which 50 are like notionally female as marked by the uh, Tarkers, and another 50 are notionally male, which are again marked by the Tarkers. Now, out of these 50, some were like gendered by definition and some were stereotypically gendered. Okay, so but for both these types of words and for both the categories male and female, like the classification accuracy was pretty high, like for all these 10 choices of the gender pairs. And the classification accuracy was measured as the following: that if the crowd has marked something as female and if that word is closer to she vector in the she he space, okay, then that is considered to be a, positive signal or a +1 in the accuracy count. Okay, so that's how they estimated the accuracy of all these 10 pairs. Now, once they have found out this nice set of 10 pairs, they have to come up with a single representation. They have to come up with a single representation. Oops, something seems to be going wrong. Single representation. From the 10 pairs. Now, a natural way to do it, and that is what they did, was to compute the principal component of these vectors. Okay, collect these 10 vectors and run PCA to get the final gender direction. Now, then once they did this PCA to identify the final gender direction out of those 10 vectors, like they wanted to see how good is the uh, like is the top principal component. Okay, so is it able to capture most of the variance in the data? Okay, or in the vectors that we were trying to combine. Is it able to do that? So in order to do that, what they did was they plotted the extent of variance explained by each of the principal components. Okay, and what they observed was the following. So here this direction tells you the component number and this direction tells you the percentage of variance explained. Basically, this is connected to the eigen value of that component. So what do we see? What do we see? So these are the different components, the principal components. So what do we see? So remember that all those 10 pairs, okay, the differences of those 10 pairs, those vectors have been crunched together to or collapsed together to obtain the principal components, that is the most important directions among those vectors. Okay, and the principal components distribute themselves as shown in this figure. Okay, as shown in the left side figure. What is it telling? So how does the distribution look? How does the distribution look? Uniform, skewed,
Skewed.
skewed. Okay, skewed. And what would this indicate?
I mean, the top component has the most
So
variance.
very good. Has explains the largest variance. Okay, so the top component is able to explain most of the variance. So we see kind of 60% of the variance is explained by the top component. Now, compared to this, if you take some 10 random vectors, okay, and from there you did a PCA and you did it like say 10 times because this is stochastic. Okay, you took 10 times you sampled such 10 random vectors and you did their PCA, then the components would be arranged like this. What do you observe from this figure? Is it skewed? Is it skewed? Far less skewed, right? Far less skewed than the left figure. Okay, so that means there is no single component that is able to explain the variance to a large extent. Okay, so there is no single representative component. No single representative component. Okay, that can explain the variance. Whereas here, if you take the top component, it actually could be thought of as a good representative for explaining most of the variance. And this is kind of the dominating direction. So this is why the authors actually chose these 10 pairs, not any random set of vectors, right? This is why the authors chose these 10 pairs, and they established first through those accuracy values, and now using this like PC analysis, that there is a single component that is dominating, and that actually explains most of the variance. Okay, now why is it good? What can we now do? Now, since we have this top component, what can we now do? What was this all drama for? What was the target? What was the question at hand that we started off with? Go back to the previous class notes and find out. What is the question that we started off with? Why were we doing all these things? Nobody recalls. Find a, I mean, if you think logically, what are these she minus he, her minus his? What are these? What
The
are these individually?
gender subspace.
The gender direction. So we wanted to, the objective was to find a gender subspace. Or simply a gender direction. Now, what do you think the authors would do now once they have done all this PCA, etc.? Have they got hold some representative gender direction? Have they got hold of some representative gender direction? So let us recall again. There were some such pairs these were all gendered pairs, and they carefully chose this pairs like 10 in number. Now out of this they did a PCA and they found one vector that explains, one vector or component that explains the variance way better than the other components. So this vector is nothing but this vector is what? This vector which is generated as kind of a summary of the 10 vectors which were like representing gender directions. This vector, which is kind of a summary, representative summary of these vectors, is nothing but the representation of the gender direction. So basically, this vector is kind of the principal component of all the gendered directions that the authors took, the 10 gender directions that the author took. And from there, they computed the principal direction in which most of them maximally align. Okay. And this like notional direction is defined as the overall gender direction. Okay. Now once they have this gender direction, like they meant a gender direction, but one can also have a gender subspace, right? You can take the first two principal components, first three principal components, whatever way you desire, and you can have a subspace rather than a single vector. Okay. So that depends, that is a design choice and is left upon the design engineer. Okay, so now once the gender direction has been defined, we can go ahead and, as I said last day, if you recall and connect, the whole purpose of defining the gender direction was to get a quantification for the direct bias and the indirect bias. So the authors wanted to quantify both of these, okay, the direct bias and the indirect bias. So again, as earlier, let us assume that N is the set of gender neutral words. Okay, and now we have at our disposal G, which is the learned gender direction. Now, using these two, we can try to express the direct bias parameterized with C as 1 by N What does this tell? This is the overall direct bias in the data computed from the individual words present in N, which are typically gender neutral words, but in many cases are having a stereotype associated with them. Okay, so now what does this measure tell? Let us go step by step. What is cos? What does this indicate? What does this indicate? Suppose this is my gender direction. Think in vector terms. How will W look like? If
Orthogonal.
cos WG is 0? Come on.
Orthogonal.
How? Huh?
Orthogonal.
Orthogonal. That means there is no overlap between them. So that means this indicates that W is not gendered. Okay. W has no gender component in it. Fine. So this indicates that a word picked up from these gender neutral words, if that word has like as like is orthogonal to the gender direction, then that means that word has absolutely no overlap with the gender direction, and therefore there is no gender component in it. Now, the other side of the coin, what would this mean? If this is G, then
Same direction and overlap.
perfect overlap. Okay, so fully gendered. So internally, think of these as follows. So basically, this W is an occupation word like babysit. And this gender direction is something of the sort of, say, she. And in this case, babysit is perfectly aligning with C. That is what is meant by W is fully gendered. Okay. And here there could be some other occupation which did not align at all with the gender direction. These are the two perspectives in which you view the thing. Now, what about that C? Now, if C is 0, what does this mean? That power there, that power factor. Again, look at the extremes. So if C is 0, what would this lead to? Huh? So direct bias is 0. And if C is 1, sorry, cos WG is 1, then direct bias is 1. However, you do not like have such strict definitions, because like a complete no overlap or a complete overlap is usually not like observed in real data. So therefore, in order to admit some variability, you set C to the simplest form possible, okay, with C equals to 1, and now if you set C equals to 1, this becomes okay. So you set the direct bias parameter to 1, and therefore your definition changes to as simple as that. Okay, so now the authors had a list of some 327 occupation words. Okay, had a list of some 327 occupation words. So these are like the set N. And they computed direct bias 1 on this data. Okay, and they found that its value is 0.08. So what do you think? So of course, direct bias is non-zero, so it exists. What do you think about the value? Small, big, very small? The extent of direct bias now with the the definition of the gender subspace or the gender direction and the uh, n words at your disposal, you now are able to perfectly quantify the direct bias present in the data set. Now, what would be your take on this number as a data scientist?
Sir, very low gender.
Very low? Sure. See, there are 327. Okay. And you are normalizing it, normalizing this value over 327. So this is the average. So at least you can say that many occupation words are indeed gendered. Okay. At least this much you can say. Now, if this is low or high, you cannot say by just looking at the mean, you also need to look into the standard deviation. Okay. Now the next part, which is more interesting. How do you capture the indirect bias? How do you quantify the indirect bias? So if you recall that receptionist was closer closer to the softball compared to football. And this was because of both of their closer association to female she. Okay, her. So this we have seen, and this was the cause of the indirect bias. Now, how do we quantify this? To motivate ourselves, think of the football and the footballer example. Okay, so in yesterday's class, we agreed that not all the similarity between football and footballer comes from their association with the male gender. Okay, so not all of their similarity come from their association from the male gender. Sorry, association with the male gender. So then it would be nice to quantify how much of their similarity comes from the association with the male gender. Can we somehow quantify that? Okay. Then, for instance, like if we can say like what is the similarity of softball with receptionist that comes from their association with the female gender, right? Can we quantify this part? So there could be other types of similarity, but then there is a similarity that is rendered between them just by virtue of their association with the female gender. And if we could quantify that part, then we can try to remove that part from the rest of their representation and see that if anything is left, then that part is the non-gendered part. If nothing is left, then it is fully, the similarity is fully explainable by the similarity with the female gender. Okay. So the idea is as follows. Now, if if I remove the gendered components from softball and receptionist, is there any similarity that is residual? Okay. If there is if there is nothing left, then the entire similarity comes from their female associationship. If still something is left, then probably it is for some other reason. So can I remove the gender related similarity part? Okay. Or in other way, by meaning by way of removing this or by way of quantifying this, can I find out what is the gender component that makes these two different vectors, softball and receptionist, similar to each other? So in order to do this, again, we need to make use of the gender subspace or the gender direction. Now we will say that let us have any word W as a mix of WG plus W norm. Okay. Now this is the gendered part of the word W. Now, how do I compute WG? Any idea? So as I say, this is the contribution from the gender. Contribution to the representation of W from the gender.
The
How do you come?
it's
Huh?
projection along the direction of the gender.
Very good. It's the projection along the direction of G, right? It's the projection of the vector W along the direction of G. This text markers are disturbing a lot. So, and that can be expressed as but then G as all other vectors are normalized. So therefore, WG reduces to so this is the gender component of the word W. Okay. So then the W norm is nothing but W minus WG. Now we define a similarity score beta between two vectors W and V as follows. What is the similarity score indicating? This is the norm, not 1. So what is this indicating? This similarity? So you have taken out the non-gendered part from WV. So what does this similarity indicate? So this similarity is only due to similarity only due to what? What is the residue when you remove the non-gendered part? What is the residue? From the whole inner product, you are removing the non-gendered part. What is the residue? The gendered part is the residue, right? So whatever similarity now could be between W and V should be just because of the gendered part, because you have removed the non-gendered part from it. So whatever similarity that might exist, whatever value beta takes up, that should be because of the similarity due to the gendered part. Okay, so the similarity is only due to the gendered part. Now, beta WV is equal to 0 would indicate what?
The gendered part is 0.
The gendered part is 0. So WG is 0 is equal to VG. Any one or both. The gendered part is 0. Okay. And on the other hand, if beta WV is 1, then the other part is 0. The entire similarity is because of the gendered part. Now, now you have quantified both the direct bias as well as the indirect bias in your data set. Okay. Gender subspace and the gender direction, more simplistically, you have been able to quantify both the direct bias and the indirect bias in your data set. Okay, so now if you see those examples that we had seen for softball and football, so let us write down once again. So for softball, extreme, we had words like receptionist, waitress, homemaker. On the other hand, on the for the football extreme, we had words like maestro, businessman. Okay. Now what we observe is that for these type of words, okay, for these type of words where beta W is always softball and the other one is a placeholder, could be receptionist, waitress, homemaker. Okay, for these values are very high. The beta values are very high. Whereas for like some random word, the beta values would be somewhere very close to 0 or even negative. Okay. On the other hand, for the football extreme, words like maestro and businessman again pretty high. So now you see you have a nice scoring metric to score both the direct as well as the indirect bias present in the data set. Okay. So once we have all this in place, now we can proceed toward our debiasing algorithm. So we'll not do the math today. Like it's a little bit time consuming. So I'll just give you the idea of what are the things that are done. So this is the last lap of the paper. Okay. So here we will do two things. One is identify the gender subspace. Meaning we will have an algorithmic prescription for this. And then we will have a second stage, which is called neutralize and equalize. Okay. So what are these? So you know already like what is a gender subspace and how one can find it. So we will define it more formally in the next class. However, the two other terms, neutralize and equalize, are new. So basically in the neutralize step, what you do is that the gender neutral words are can you tell me what is done? The gender neutral words should be should be zero in the In the what? Gender neutral words should be ideally 0 in the what? This is all we started off with. In the gender subspace. That is, there should not be any gender component for gender neutral words. That's why they are gender neutral, right? Gender neutral words should no longer have any gender component. Okay. Once you generate your new embeddings, in these embeddings, the gender neutral words should not have any gender component. Okay. That is what is the idea. So in your new embeddings, gender neutral words should have no representation in the gender subspace or direction. So basically, think of it like this. Anyway, basically think of it like this, that this is your gender direction. This is that something that does not have any gender component. And if there was a word like doctor here, after you have debiased the new embedding for doctor will go inside here. Okay. So that is what is the idea. Now the other part, equalize. What is equalize? Any neutral word, any such gender neutral word should be equidistant from all the equality sets. Equality sets meaning male, female, actor, actress. Okay. So basically what they are telling is the following. Suppose you have debiased babysit. Okay. Now, and then there is a equality set guy, comma gal. Now babysit, after it has been debiased, it should be equidistant from both guy and gal. Similarly, babysit should be equidistant from grandmother and grandfather. So this is the overall idea of the debiasing algorithm. Next week, we will, in Wednesday's class, we will finish off this paper. We stop here.